So we start solving our sheet number 9.2, which is all about functions of more than one independent variable. That's new, because up to now, even inside our sheet number 9.1, we've been talking about, well, higher dimensional situations, okay? But on the other hand, we still were able to express everything with a single independent variable, which is called t, as you remember from just before. And so there was no need to introduce any new kind of taking the derivative for a certain, with respect to a certain variable, since as soon as we have more than one independent variable, we must take care when taking the derivative, what do we do with the other variables? Do we ignore them? Do we keep them constant, or something like that? And as you know, because you've learned it, it turns out, introducing the so-called partial functions, etc., there is a clear and simple method of taking the derivative of such functions exclusively with respect to one of their independent variables, keeping all the other independent variables constant, which means really treating them as if they were regular constants. That's what we do. And now we look at these two examples of so-called scalar fields. I have decided to introduce this phrasing right now because it's very important to understand what scalar fields are and also then what vector fields are, especially in 3 dimensions. But I allow myself and ourselves to use this same phrasing also in the 2-dimensional case, which is actually absolutely correct, even if you think of an appropriate application, which could be in the electrical domain, sort of, just imagine a plane, like, let's say, a plastic plane, which has been electrostatically charged. So you have a certain distribution of electric charge in a plane. And this would be described by a so-called electrical potential function, which is really a scalar because non-directed, as you know, potential energy in joules per Coulomb, for example. So this would be electrical potential in a 2-dimensional case, and we call it a scalar field. Field means as much as it's some mathematical function that's defined everywhere in a given vector space. So you know what I'm talking about. Also, another good example would be, imagine a temperature distribution in the plane. Like you use your cooking device and you just made some soup, and then you find out that it's the plane area there is still hot, especially in the center of where you've been cooking, and but the temperature decreases sort of from point to point to the outside, and this can be described very well by a scalar temperature field in the plane. And it would be interesting to find out mathematically in which direction and how strongly does the temperature rise when you, for example, when you approach the center of heat. Things like that. It's very broad field of application that we find here. Okay, so let's just look at this in a little more abstract way now for the first, and say these scalar fields in 2 dimensions are just given. There is, by the way, oh yes, I missed the closing parentheses here, but I already corrected it in my version. I hope I can upload it soon. Now, it's possible to visualize such functions even more, let's say, vividly by assigning the z coordinate to the vertical direction, as you are all familiar with. If we take a perspective view, like the usual one is, this should mean that the x-axis points towards yourselves, the y-axis to the right, and the z-axis to the upwards. Okay, so now it would be possible to, and it is possible actually, visualize this function by using a sort of a curved surface which spans, you could say, along the XY plane or above the XY plane. It's a little hard for me now to sketch this, but just imagine something like this, okay? Like a plane hovering over the XY plane. And it's not really a plane, it's a curved surface hovering over the XY plane. Also, it can sometimes be positioned below the XY. You know what I mean? It's possible to visualize it in this way. And this is what we're doing in the next exercise. You could also do it now, but it's not necessary to solve this exercise, yeah? So what do? We just train the technique of taking partial derivatives. And since we have only two independent variables, we will take the partial x derivative first and then the partial y derivative. But just remember, you always start from scratch, not from scratch, but you always go back to the original term when differentiating by another independent variable. So, and also the first point is to get familiar with this kind of field. We should find out which is the maximum possible domain of such a function in the two-dimensional case, okay? So two-dimensional domains are by itself something new. So it's worthwhile being concerned with them for a moment. So what's the domain of this first example function? Well, we all know that the positive square root can only be taken with non-negative arguments. So this is all we demand. We demand that the square difference of x and y coordinate is greater or equal than 0. That's what I write here. So if I just rearrange this little unequation a little bit, or inequality as it's called, I get that x squared must be greater or equal than y squared. And even simpler, I can say this means that now again, the vertical bars are here, as we know them. The absolute value of x must be greater or equal than absolute value of y. So now it's a good training, I think, to try and sketch this two-dimensional domain in the xy plane. So this is sort of looking from above, yeah. And this is the more correct sort of set theory notation for the solution here, which says that the domain is equal to the set of all pairs of x and y, element r squared, r2, however you call it, you know, holding or fulfilling that absolute square of x is greater or equal than absolute square of y. So that's the more formal notation. So now looking at this, I use the following method. Since this includes the special case of equality, I can look at this case first. The special case is that, absolute value of x equals absolute value of y. We know what it means. By taking away the vertical bars, we need a case distinction, and we find out that x must either be positive or negative y. So that's all. X and y can only differ in sign, but they cannot differ in the value, okay, as such. You know what I mean? And so since we know the first case, x equals y, is simply the first of these, how are they called? I sometimes forget, bisector, right? These bisector line, and this one, the first one. And the second one is the second bisector line, which represents x equals negative y. So these two blue lines quite surely include or are included in the domain. Now the question is, how do we get from the equal case to the greater case? And now you must understand, since the greater sign means that the absolute value of x overweighs that one of y, you could say, it means that you have to move away from these blue lines in a direction where the number value, ignoring the sign of x, increases. You see what I mean? So I go from this region, I go to the left, because the if I read the numbers here, I see they are increasing. I'm just ignoring the sign, the negative sign, okay? And on this side here, of course, I have to go to the right. So this is what my sketch really represents. It represents the area where this function is well defined, so that you could say that the forbidden area would be everything that's not in color here. So like this would be the forbidden area in this. Okay, so I think it's clear what I'm saying. What's that? So I have some disturbance. I just mute you for a moment. Okay. So let's proceed. How to take the partial derivative with respect to x. Now, interestingly, or well, let's say conveniently, all the derivation rules which are familiar to us still hold. So it means, since this is a chained expression, okay, so it's composed, it means I always have to take the outer derivative first. And since we have known for a long time that the first derivative of the square root is always 1 over 2 times the square root. This is what I'm using here. You should look at it like this. I'm first taking the reciprocal of 2 times square root of the argument. And then, only then, I will multiply the inner derivative by the chain rule. And as you know, since we are taking the partial derivative for x, as I shortly say, when I say derivative for x, I mean derivative with respect to x, or as Martin wrote, I think, according to x, okay? Now, I can see that x squared gets differentiated to be 2 times x, but this time, the subtraction of y squared counts as an additive constant. We treat, as I told you, we treat every other variable as to be really a valid constant. So it's like if there was written minus 17, and it just, well, it disappears because I'm differentiating with respect to x. So that's all, 2 times x as a factor, and that's why I put it in this form, and finally I canceled out the factors of 2 here. So what remains is actually just x in the numerator and the square root of this square difference of x and y in the denominator. The same holds almost analogously for y, because now this time I take the first partial derivative for y, which means again to start at the outside, so that derivative of the square root is 1 over 2 times the square root, but then I have to multiply the inner derivative this time with respect to y. So it means that x squared counts as an additive constant now, while the minus sign stays there, and y squared gets differentiated to be 2 times y. Again, I cancel out the factors of 2, and I get negative y over same square root expression. Now, it's not part of this exercise, but anyway, I just use the opportunity to show you. It is, as I explained with my temperature example before, it is very well defined what the so-called gradient is, for example, in a planar temperature distribution or electrical charge distribution. The gradient is always a vector which gives you the strength and direction of a maximum function increase. That's all. And this is, in this case, so the gradient generally is put up very easily by constructing a vector that consists of as components of the different partial derivatives of your term with respect to your independent variables. So since we have a common scalar prefactor here, which is 1 over the square root of square difference xy, this one, we can really pull it as a factor. We can pull it before the expression. What stays in the vector is x for the first and negative y for the second component. So this is quite interesting by itself, since it's well, you could relatively easily even make a little sketch where you see the geometric structure of this gradient field, which it already is. This is a whole field because you have a valid vector for any point in the xy plane, and that's why we talk about gradient fields actually. So that's an interesting topic by itself. But the exercise is done so far. In the next example, well, I like it because it's this time it's even more vividly possible to visualize it. So you all remember the most important aspects of polar coordinates. You all remember our usual transformation equations for complex numbers, okay, polar form, Cartesian form, things like that. So you should all remember that this famous arctangent expression of y over x, no matter whether it's used in the real domain or in the complex domain, it always represents this magical value of phi, which we have defined as to be the angle with respect to the positive x-axis. You remember, not to be seen in this graph, more in this case here. So it's phi, and if you understand, I'm going back to my picture from before. I'm sorry, I have to show you again here. Oh no, although it's not given here, I interpret this to be a three-dimensional visualization, or I imagine a three-dimensional visualization where z is the vertical component as I sketched it before. So I'm asking myself, which kind of curved surface could it be that is represented by this function? And there it turns out it's a famous such curved surface, which is also called a screw surface. You may know what I mean. Like really, I'm talking about a screw as a tool, a metallic screw, which has this helix-like structure as a surface. You know what I mean, okay? So why is it? Well, it's because z is much the same as phi in this case. So just imagine you would take a radius vector here with a certain angle, phi, to the x-axis, and then you would assign this angle to the z coordinate, which points towards you. It means the more you turn this vector against the clock here, like counterclockwise, the higher your z, the larger your z component will get. And this is like sort of constructing a screwed staircase. Let's say, how do you say? A spiral staircase. That's how you call it. Spiral staircase, right? So that's what we do, but it's you could say it's a spiral staircase without steps, a smooth spiral staircase, really. But now there's a little restriction to what I'm saying, because the arctangent has a very restricted codomain. You may remember, this is it. It has a connected graph. That's quite nice to know, because what is it? It's just the mirrored version of the central graph. Well, let's say the central branch of the famous tangent function. As you remember, the tangent looks a little bit like it has this central branch, and then it repeats periodically, pi periodically, by the way, and you have these poles always with the sign change at multiples of pi half. So that's well known, and taking the mirror at the bisection line, you know what I'm talking about, because this is the inverse function. So this is what you should know from school, all about these things. These properties of these functions. Now, interestingly, it's the domain is not restricted for arctangent of x, which means that it asymptotically reaches its maximum value of pi half in the positive domain and negative pi half in the negative domain. I'm talking about the simple arctangent of one argument, but now we have the arctangent of this combined argument, and that's what makes it a little bit tricky. So in the end, I find that the domain of our two-dimensional function will be the set of all pairs of xy element R2 fulfilling x unequal to 0. That's actually all, because only if x were 0, I would have a division by 0, which is not possible and not allowed. Honestly, even at least in the limit case, if I cautiously would x allow to approach 0 from positive values, I would get something like approaching positive infinity, or in the other case, negative infinity. And in the limit case, I would even have a valid codomain value of pi half or negative pi half. So but let's just leave it away. The more important point is that in the so what does it mean? First of all, it means that the whole y-axis is the forbidden zone. So that's why I drew it in red color here. Okay, you understand what I mean? Forbidden area. Okay, like area 51. Little joke. Yeah. So here it's well defined. Here it's well defined, and actually you would have what I was talking about. This sort of spiral staircase. It would just develop from below the xy plane here, and then spiraling up to a height of pi over 2. And then the same thing would happen again. It jumps down and then it rises again. So that's not really a valid screw surface. It's just sort of a certain fraction, 2 fractions of a screw surface. Don't care. Let's take the let's solve the exercise, which is finding out how do I take the first derivative of this expression with respect to x and then with respect to y. And to this end, I told you here that the arctangent of x has the derivative of 1 over 1 plus x squared. This is a very well-known and famous equation or identity, which you find in all the differentiation handbooks. So that's what we use. So now it means this time the outer derivative of this term will be, by the scheme, 1 over 1 plus argument squared. So it's 1 over 1 plus this argument squared, where I put y over x in parentheses and then squared. So that's the first step. But again, like before, I must multiply the inner derivative, firstly for x. And now I must be careful. Perhaps you make a little side note to this end. I would rewrite this as to be y times x power negative 1, and then differentiating, but treating y as a constant factor. I get negative 1 times y times x power negative 2. And that's what I did in the end, okay? This is negative y over x squared in the numerator and the denominator as explained. So this doesn't look so really nice. It's like a nested fraction. I would like to simplify it. Well, it's easy to do so. First of all, I would say we might, what do we do? Yeah, we might pull this divisor of x squared in the main denominator, first of all, yeah? Then I might, with this expression, I might remove the parentheses, so I get y squared over x squared. So that's quite simple. The minus sign has been pulled before the fraction now. Y stays there. So, and then it's possible to easily expand this fraction with a factor of x squared. No, not even, sorry. I just have to remove these parentheses as I see, x squared times 1, right? And then here it cancels out and it gets x squared plus y squared, which is very nice because it's the squared sum of x and y, which is always the squared distance from the origin in the plane, by the way, and negative y as a factor. This almost the same thing again happens. It looks differently. It looks quite different, but it turns out to be quite similar in the end when I differentiate with respect to y. Let's do so. Arctangent, again, from the outside, differentiated over its own argument, or with respect to its argument, gets me 1 over 1 plus argument squared. That's the same as before. I just did not use parentheses anymore. Now this time it's more easy to take the inner derivative because this time y counts as a independent variable, while the divisor is dividing by x. counts as a constant factor, or yeah, let's say factor of 1 over x. So I can just keep this 1 over x. It's just not touched, treat it as a constant. Y is differentiated to be 1, so I get 1 over x over this expression from before. This time it makes sense to expand the fraction with a factor of x. So times x in the numerator gets me 1, times x here. Now I must be careful. I get x, 1 times x is x. And here I get y squared over x. So actually, in the end, it would have made more sense. Oh, okay, I could also have pulled down this divisor of x much the way I did before. So that's what I actually did. And now it makes sense to expand the fraction with an additional factor of x. In the numerator, 1 times x gets x. And here it gets x squared, and this x disappears. So very nicely, I get x over x squared plus y squared. Again, we can, if we agree to look at the gradient for short, we can pull out this factor, the scalar factor of 1 over x squared plus y squared, which is just a scalar, a scaling factor outside, so that inside the vector remains negative y, x. This is more interesting even than before. Look, here we had x and negative y, this time negative y and x. Why is this more easily to be understood? Well, you all know there's a very famous trick in, I don't know this here, a trick known from 2D vector algebra, let's say, namely constructing, well, you just remember, constructing a vector which is perpendicular to another given vector. Let's say I have a vector of AB, and I am searching for a vector which is perpendicular. So the easy trick is exchange the coordinates and take a minus sign at one of them. It doesn't matter where, I can decide to take it here. So you see, it's exactly the same structure. Why are these two vectors perpendicular to each other? Easily, because their scalar product equals 0, right? A times negative b plus b times a equals 0. So that's for the same reason we can be very confident that the gradient is always, in this case, in this function, always perpendicular to the radius vector itself. And this leads me with, well, allow me just to make it short. This leads me to the conclusion that anywhere I go in the plane, when I use a radius vector to, for example, to construct any of these gradient vectors, I always, from where I am, coming from the origin, going anywhere, I go in a right angle from this point, counterclockwise, by the way, and construct my gradient. Shortly speaking, what you see in green, very, very small scaling, of course, I hope you can recognize it. What you see here, this is, you could say it's a so-called gradient map, okay? It's a map of the gradient of this function. And before I told you, firstly, what the gradient means, it's the strength and direction of maximum increase of such a function. And now, since meanwhile, we interpret it as to be a spiral staircase without steps. The question is, and I give you the answer, the question is, where must I go in order to rise as, let's say, as quickly as possible when I'm moving on a spiral staircase? Without steps, by the way, a smooth spiral staircase. The answer is, as you all know, you must go around. You must go around the z-axis all over again, against the clock, okay, like counterclockwise in the mathematically positive sense. So, and also second point, you must, if you really, just imagine it's a contest, and the question is who arrives first at the top, then it will be a good idea to walk near the axis of this spiral staircase, right? Because the nearer to the axis you're walking, the steeper you will be going upward. It's a fact. So, and that's why the gradient vectors here near the origin, well, aside from being arranged in circles around the origin, which is clear, they get stronger, they get a longer, bigger absolute value the nearer they are to the origin. So this is a very nice picture of what happens on such a curved surface when you try to rise as much as possible in the z direction, which is pointing towards you. I hope it's very vivid for you now to understand what it all means. And also you see, why are these ones longer, nearer to the origin? Well, just because this inverse squared distance from the origin gets larger, right? And the direction is determined by this perpendicularity, okay, as I told you. Now, that's it.